This video is brought to you by mywayteaching.com.
Next, consider problem if water vapor is assumed to be a perfect gas. Okay, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoule per mole. Calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius and 1 mole of water is converted into ice. So first consider the first case. Okay, I will consider the first case. The change means from H2O, that is liquid, to H2O of gas. So see, question, water is vaporized, assumed to be a perfect gas, means from it is converting from liquid to gas. So internal change in energy delta H, we know the formula, delta U plus delta Ng into RT. Or now you want a change in internal energy, so that you can write, okay, minus into delta Ng into RT. So substituting the values, sub values, okay, that is delta U. Okay, we know that delta H, we have to write delta H means in given, they have given 41 kilojoule per mole, okay, minus delta Ng into 8.3 joule per mole per kilo, where temperature 373 Kelvin. So after multiplying and after calculating all this, 37.904 kilojoule per mole is the answer for first one. Like second one, question for second is 1 mole of water is converted into ice. Then now calculate what happens. 1 mole of water is converted into ice, means it is converted into solid. So we can put, therefore there is negligible change in volume, so we can put P into delta V is equal to delta Ng into RT is equal to 0. So in this case, delta H is equal to delta U. So delta U is equal to 4100 kilojoule per mole is the answer. Next, extensive and intensive properties. Okay, so what do you mean by an extensive property and what do you mean by an intensive property? An extensive property is a property whose value depends on the quantity or size of matter present in the system. See, it depends upon the quantity or size of the matter in the system. And here I will give the example for this one extensive property. Example is mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. I will write mass, okay, then volume. Next, those properties which don't depend on the quantity or size of matter present are known as intensive properties. Okay, So let us understand the distinction between extensive and intensive property by considering a gas enclosed in a container of volume V at temperature T. This is figure A. This is figure B. So in figure A, a gas at volume V and temperature T. At volume V and temperature T, it is a partition, each part having half of the volume of the gas. Okay, so now let us understand the distinction between extensive and intensive properties by considering the gas enclosed in a container of volume V and at temperature T. Let us make a partition such that volume is halved in this figure, as shown in this figure. B now has half of the original volume V by 2, but the temperature will still remain the same, that is T. It is clear that volume is an extensive property and temperature is an intensive property. See here, volume only partitioned here, V by 2, it is halved. So that volume is called extensive property. So that volume is called extensive property and temperature is called intensive property. It remains same. Intensive property. Okay. Next is heat capacity. In this subsection, let us see how to measure heat transport to a system. Okay, this heat appears as the rise in temperature of the system in case of heat absorbed by the system. The increase of temperature is proportional to the heat transport, that is Q is equal to coefficient into delta T. The magnitude of coefficient depends on the size, composition and nature of the system. We can also write it as Q is equal to C into delta T. C called coefficient is called heat capacity. C is called the heat capacity. Now C is equal to heat capacity. Okay, and now we can measure the heat supplied by monitoring the temperature rise, provided we know the heat capacity. When C is large, when C is large, a given amount of heat results in only a small temperature rise. Water has a large heat capacity, that has a lot of energy is needed to rise its temperature. Okay, C directly proportional to amount of substance, the molar heat capacity of a substance. C is directly proportional to the amount of substance. The molar heat capacity Cm, that is equal to C by N. Substance is the heat capacity for 1 mole of a substance and is the quantity of heat needed to rise the temperature of 1 mole by 1 degree Celsius. Specific heat, also called specific heat capacity, is the quantity of heat required to rise the temperature of 1 unit mass of a substance by 1 degree Celsius. Specific heat capacity. What do you mean by specific heat capacity? Okay, what do you mean by specific heat capacity? Means is the quantity of heat capacity it is required heat is required to rise the temperature of 1 unit mass of a substance by 1 degree Celsius. Okay, for finding out the heat Q required to rise the temperature of a sample, we multiply the specific heat of the substance C by the mass M and temperature change delta T. So that Q can be obtained C into M into delta, sorry, C into M into delta T, means for finding out the Q heat. Okay, so we are of the required to rise the temperatures of sample, we multiply the specific heat of the substance C by the mass M and the temperature change delta T. The relationship between Cp and Cv for an ideal gas. So what do you mean by Cp and what do you mean by Cv? Do you have any idea about Cp and Cv? At constant volume, the heat capacity C is denoted by Cv. Okay. What? At constant volume, the heat capacity C is denoted by Cv, and at constant pressure this is denoted by Cp. At constant pressure, which is denoted by Cp, we can write equation for, so let us find the relationship between these two, Cp and Cv. Okay, now at constant volume we can write the equation for heat. We can write the equation for heat, that is Q at constant volume as QB is equal to Cv into delta T is equal to delta U. Like at constant pressure, as Qp